Hello. In this video, I'll give you a high-level overview of the two main cryptographic ingredients in Bitcoin, the SHA-256 hash function and the ECDSA signature scheme. I'll also give you a glimpse into how these ingredients are used in Bitcoin. We'll dig deeper into the details in the next video. Let's begin with hash functions. A hash function is a function that maps inputs of arbitrary lengths to outputs of a fixed length. The description of the function is public. For any input string m, h of m is computed by mixing and mangling the bits of m in a complicated fashion, so that the result h of m bears no resemblance to m itself. So an example is this message being hashed to this random-looking value. H of m is called the hash of m. SHA-256, where SHA stands for Secure Hash Algorithm, is a hash function designed by the US government's National Security Agency in 2001. So the hash function is now 20 years old. SHA-256 produces hash values that are 256 bits in length. Here are two examples. I've hashed the message, hello there, and the result is this random-looking string, which I've written in hexadecimal. 0x stands for hexadecimal, and the hash value has 64 hexadecimal digits, which correspond to 256 bits. Note that the hash value bears no resemblance whatsoever with the actual message. Here's the hash of a similar message, hello there, where now the T has been capitalized. This is the hash value of the second message. And notice that the two hash values bear no resemblance whatsoever to each other, even though the corresponding messages are almost identical. So changing even one character of a message changes its hash value in a completely unpredictable manner. Bitcoin uses the notion of proof of work. As the name suggests, proof of work is a mechanism whereby one party, called a prover, can prove to a second party, called a verifier, that she has performed a certain amount of computation. The verifier can efficiently verify the proof without having to do all the computation that the prover did. SHA-256 can be used as follows for proof of work. The verifier sends a message m to the prover. The prover's task is to find a number n called a nonce, so that h of m and n begins with, say, 40 zeros. Here the comma denotes concatenation. So h of mn is a hash of the message obtained by concatenating m and n. The fastest method known to find such a nonce n is to pick an arbitrary number n, compute the hash of m and n, and check if the result begins with 40 zeros. If it doesn't, then select another n and repeat. Assuming that h behaves like a random function, the probability that h of mn begins with 40 zeros is 2 to the power minus 40. And so the prover can be expected to perform 2 to the 40 hash computations before she finds a nonce such that h of mn begins with 40 zeros. When she does find such a nonce, the prover gives n to the verifier. The verifier computes h of mn and checks that it begins with 40 zeros. Notice that the prover performs 2 to the 40 hash function computations on average to find a nonce. On the other hand, the verifier performs only one hash function computation to verify the nonce. So the nonce is the efficiently verifiable proof that the prover has performed a certain amount of work in this case 2 to the 40 hash function computations on average. Of course, the number 40 can be replaced with any number L to prove that one has performed 2 to the L evaluations of the hash function on average. In Bitcoin, miners are entities that verify transactions received in a 10-minute window. The miner compiles a block that contains the verified transactions, denoted here T1, T2, T3, the SHA-256 hash of the previous block, so this value here, and the SHA-256 proof of work, N, the nonce. So in other words, the hash of the message comprised of the hash of the previous block, the transactions, and the current nonce must begin with the prescribed number of zeros. This list of blocks is the Bitcoin blockchain, which is replicated and stored across many parties on the internet. Notice that if the data in a block is changed even in a single bit, then a new proof of work would have to be generated for that block to be valid, and indeed for all subsequent blocks to also be valid. So for example, if a single bit in this block is changed, then its hash also changes, which means the new nonce has to be generated before the hash of this block begins with the prescribed number of zeros. And when this nonce is changed, so does the hash of this block, which means the input to the next block also has changed, and so its nonce also needs to be generated. And so changing a single bit in any block of the blockchain means that its nonce and nonces of all subsequent blocks also need to be generated. And that would be a lot of work. And so proof of work is how the integrity of the Bitcoin blockchain is maintained, even though the blockchain is stored by untrusted parties across the internet. The second cryptographic ingredient we need is a digital signature scheme. Signature schemes let someone digitally sign a message so that the authenticity of the signed message can be verified by anyone. Every user of the system, say Alice, has a public key capital A and a corresponding private key little a. As the name suggests, Alice's public key is publicly available to everyone, whereas she keeps the private key secret to herself. To sign the message M, Alice runs the signature algorithm on the message and her private key. The algorithm mixes up the bits of M and A in a complicated fashion to produce a signature S. Anyone can then verify Alice's signed message MS using a verification algorithm. This algorithm takes as input the message, its signature, and Alice's public key. The algorithm outputs accept if Alice did indeed generate the signed message. Otherwise, it outputs reject if Alice did not generate the signed message, and so the signed message is an attempted forgery. Notice that Alice is the only party who can generate signed messages that are accepted with the verification algorithm and her public key, since Alice is the only party that knows the corresponding private key to be used in the signing algorithm. Notice also that unlike handwritten signatures, Alice's signatures depend on the message she is signing. So a forger is unable to generate a valid signature for a new message M primed, even if the forger has already seen many signed messages that were generated by Alice. Let's move on to the ECDSA. The elliptic curve digital signature algorithm, ECDSA, is a signature scheme that is widely standardized and deployed. Bitcoin uses ECDSA with the elliptic curve y squared equals x cubed plus 7 modulo p, where p is this nice 256-bit prime number. There's a fixed point P on the elliptic curve, so P has coordinates x and y, where x is this large number and y is this large number. One can check that this point satisfies the equation of the elliptic curve. This curve has a large number of points. In fact, the number of points is n, where n is this large prime number. This elliptic curve was chosen by researchers at BlackBerry Certicom in the late 1990s. It's a special kind of elliptic curve called a Coblets curve. These curves were popularized by Rob Gallant, Rob Lambert, and Scott Vanstone, who designed fast methods for doing arithmetic with points on these curves. I'll next describe ECDSA key pairs. Alice selects a random number a between 1 and n minus 1. Recall that n is the number of points on the elliptic curve. And she computes the elliptic curve point capital A, denoted little a times p, which is p added to itself a times. She can do this efficiently. The point capital A is Alice's public key, whereas the number little a is her private key. Computing the private key from the public key is an instance of the elliptic curve discrete logarithm problem. This problem has been intensively studied for more than 35 years, and the fastest method known for solving this problem requires roughly 2 to the power 128 operations. This is a completely infeasible amount of computation. And so, given Alice's public key, no one else is able to compute the private key from that public key. And so Alice and no one else can use the private key little a to sign messages, whereas anyone who possesses Alice's public key capital A can verify the authenticity of these signed messages. I won't describe the ECDSA signature algorithm and verification algorithm in these lectures. The details aren't important to us. Here is an example of an ECDSA key pair. Recall that P is this fixed point on the curve xy, where x and y are these large numbers. Alice selects a random number a between 1 and n minus 1. Let's say she selects this number a. So this is Alice's private key. Then her public key, capital A, is the point P added to itself this many times, which works out to the point xy, where x and y are these large numbers. So this is Alice's public key, whereas this is her private key. Computing the private key from the public key is an intractable computational problem, and so the private key is indeed private to Alice. Alice uses this number to sign messages, whereas anyone can verify her signed messages using this public key. Alice, whose public key is capital A, can give a Bitcoin to Bob, whose public key is capital B, by signing a message with her private key A of the form, the owner of public key A hereby gives 1 Bitcoin to the owner of the public key B. So in Bitcoin, a transaction is a signed message of this form. Anyone can verify that the signed message was indeed signed by Alice, using Alice's public key capital A. And they know to use capital A because capital A is in that message. In order to give the Bitcoin he received from Alice to another user, Chris, say whose public key is capital C, Bob would sign a message with his private key little b of the form, the owner of public key B hereby gives 1 Bitcoin to the owner of public key C. So to give this Bitcoin to Chris, Bob signs the message with the private key corresponding to the public key that is in that message. Chris and other people can verify the authenticity of this signed message using the public key B, which is in that signed message. Notice that this public key is the same as this public key. So in the first message, this is the receiver public key. In the second message, this is the signer's public key. Similarly, Chris could then give this Bitcoin to another party, and so on. The public key A serves as a pseudonym for Alice. Notice that the message does not contain Alice's name, but only her pseudonym. This gives Alice a degree of privacy when she makes the transaction with Bob. Indeed, Alice can select a different key pair for each of her Bitcoins. This can increase her privacy because it is more difficult to link her transactions made with different public keys. We'll see the details of Bitcoin in the next video.